Welcome back to Codex. Our speaker today is Courtney Paquette, who's an assistant professor at McGill University. Courtney Paquette is an expert in algorithms for optimization and data science, and today she'll tell us about the dynamics of stochastic gradient descent. Take it away, Courtney.
Yeah, so first of all, thank you to the organizers for inviting me. I'm excited. This is looks like a really great seminar that you guys put together. And also, before I begin, please ask questions, slow me down. If things are unclear, I'm happy to explain. There's quite a bit of stuff in here. So, all right. So as was noted earlier, this is a little bit of a pun on the title. So we're going to look at hitting the high dimensional nodes in ODE for SGD. This has been a project that I've been doing with a lot of different people, from Google DeepMind to students at McGill, now who are at Harvard, PhD students, etc. I hit the wrong button. All right. Okay, so what are some of the challenges and problems that we kind of see in optimization for machine learning? And hands down, I would say that the biggest is that there's this big gap between what is actually happening in theory versus what is actually happening in practice. So if practitioners, usually in machine learning, kind of just ignore everything that theoreticians say. This is even more so in machine learning than other areas, I feel like. And on the other hand, theoreticians, which is kind of what I view myself as, well, we produce these great theorems and stuff like that about how the dynamics of certain algorithms work, but then we produce pictures which look like the thing on the right here. So what is this picture on the right? Well, this is runs of an algorithm, so that's what the gray lines are, okay? And it's number of iterations versus suboptimality, say, distance to optimal or function values. And then we say, well, here's what we would produce for our worst case, which is the blue. But, in practice, it always seems to work better than our worst case, what our bound always says. And I'm giving a lot of credit to this blue curve here, because in reality, actually, this curve is like not even on the same order of magnitude. Like, it's just completely off. And yet we still always say, hey, it looks better in practice, and we leave it at that. So, what this talk is really going to be about is saying, like, wait a second, instead of just say, hey, it works better in practice, which it always seems to do, let's go back and say, what's wrong with our current theory? Meaning, basically, we sort of have a mismatch of our assumptions with what is actually happening in reality to the problems that we're trying to solve. Okay, so the goal again today is to look at the gap between the theory and the practice and sort of better understand some of the assumptions that we're actually using in these machine learning algorithms. Okay, so if there's anything you guys get out of this talk, it's hopefully this picture, which is this idea that we can actually predict, without ever actually running a stochastic algorithm, the dynamics of, say, SGD. So we can predict it without ever running it. Okay, how do we do that? Okay, well, I can't just, do it without some information. So here I'm going to assume things like spectrum of the Hessian that I have access to. I have access to, say, the targets and the initialization. And so on this picture on the right here, this is on a real data set. This is CFAR, so these are images, classification of images. And I'm running in my SGD algorithm, so it's the number of iterations and, say, distance to optimality. And what you'll see is the squiggly lines are actually what SGD is producing, and the straight curve line is my total prediction. Okay, so I predicted that curve without actually ever running it, even using real data. Okay, usually this gets like an awe, like, how is that possible? It's a stochastic algorithm, all sorts of things. How can you do it? So let's see why it works. Okay, so we started this question with saying, like, what are some of the assumptions that we need to make to maybe rethink? So let's go back to what sort of typical machine learning problems look like. So they generally take a specific form where they have sort of a large finite sum, where you're minimizing some x in some d, which I'm going to say is the number of features, and n being the number of samples, so your data points. And what I'm going to say for many machine learning problems is that they're high dimensional. So what I mean by this is that they have a lot of features and also samples. So just to give you a perspective, this is actually now very out of date because this is Chat GPT 3. For instance, you see that like in those models, it has about 175 billion parameters. So that's your D. Okay, so it's pretty big. Now, the other thing which is kind of unusual is that for many machine learning problems, we're not in what I will call classical statistics. Classical statistics is kind of like you fix the number of features, D, so the space that you're minimizing over, and you let the number of samples go off to infinity. Why is that? Well, if you actually look at what the current state-of-the-art models are, and you plot sort of parameters, D versus number of data points, what you'll see is that there's actually sort of a linear relationship between the two. That is to say that as we increase the number of samples, we're also somehow increasing the space that we're minimizing over. So in fact, the regime that these machine learning problems are working in is sort of this proportional regime, where both N and D are growing, but proportionally to each other. If you want to think of this, you can think of this as like a matrix where you have rows and columns. And what's happening is that if you add a row, you also have to add a column to your matrix. That's how you're growing the matrix. We see when you grow matrices like that, they behave very differently than if you have very long and skinny matrices, which would be more of the classical statistics view. So what sort of makes high dimensions different? So the simplest answer is that the more room you have, the more possibilities for your input. So say an input which generates kind of the worst case complexity can be really, really far from typical. And you might then say, well, if we want to make this assumption that we have high dimensionality, how do we actually capture high dimensional structure in our problems? Well, it is quite difficult, but we use a little trick from theory from statistical learning where you kind of put a probability distribution on your input. Okay, so you put this probability distribution on your inputs, and then you analyze what the complexity is. Okay. All right, everyone clear? Setup? Okay, so here's what we're going to study today, the type of problem. So I'm actually going to switch a little bit. I'm going to do the expected risk problem, which is that I'm going to be minimizing a risk function, which is the expectation over my data, A, okay, which I'm going to assume for the moment is normally distributed with a covariance K. And I'm just going to assume that my covariance has an operator norm which is bounded and doesn't depend on any dimension. All right. I'm going to let epsilon here be like label noise. So this is targets get a little bit perturbed by some noise. And x star here, well, for the moment, just think of x star as a fixed vector. Okay. So the idea behind the problems that I'm going to be looking at is I want to impose that machine learning problems sort of have some high dimensional structure built in the sense that they look like compositions of a high dimensional function with a low dimensional function. So here I'm going to think of F as being low dimensional and my data A being very high dimensional. So I'm going to take A to be inside D, RD, and what's going to happen is I'm going to hit it with this X. A transpose X is going to do some sort of averaging, so it's going to put it into a low dimensional space. So I'm going to assume A transpose X is actually low dimensional. And then I'm going to apply some function to it. F is some low dimensional function. Is this clear? So you have this D, RD, that's the space that your A is. It's very large. You hit it with something like X. When you do A transpose X, it shrinks it down to a smaller dimensional space. Okay. So what does this allow for? It allows for lots of things. Lots of stuff looks like this. So for instance, any kind of generalized linear models, okay? Multi-index models. Multi-index is just a fancy term to say that your M here can be more than one dimensional. It allows for things like multi-class logistic regression. So in this case, M would be the number of classes. And this X star, well, it's just you can think of it either as a ground truth signal, it can represent mean of data, or just some fixed vector. It's kind of not the thing you're minimizing over, but we wanted to allow some flexibility in our modeling. Okay. All right, so what are we gonna run? So the classic algorithm that we're gonna look at is one pass SGD. So the idea here with this is that at each iteration of the algorithm, we generate a new data point. So we generated A, okay? And we just update our gradient, not by taking grad R, but just taking grad sort of the inner thing evaluated at this one data point, right? And what you see here is that for large models, as both the parameters and samples go to infinity, but the ratio is going to some fixed constant, that the risk evaluated at this stochastic algorithm actually will converge to a deterministic smooth function. All right. This function is completely analyzable, and it's determined just by the spectrum of the covariance matrix of your data. Okay. That's what you actually see in this picture on the left here. So this is logistic regression. So I'm plotting the population risk of it, or the KL, you know, KL. And on the x-axis is the SGD iteration. What am I doing here? Well, I'm running SGD, okay, doing it, and I'm plotting in the shaded region the variance of each run, okay, the variance of the runs for various D sizes. So I start with D is equal to 100, then I increase, that's the blue, etc. And what you see is that the variance of the runs is actually shrinking as you increase dimension until it hits this red curve, which is just a theory that you can completely predict. All right. So there's a concentration result. So why do we see this concentration? And how can we do this prediction? So the first answer is why we see it is that we have this sort of extra averaging effect just as a result of taking a high dimensional vector A and hitting it with X. So there's averages out in D and it becomes something low dimensional. So there's already this weird concentration result. How do you actually get a prediction for the dynamic? Well, we need something more. We need to have something which we can define through some ODE. We need some sort of low dimensional statistics which sort of describe all the dynamics that we see of the risk. And it turns out you can do this in this problem. So what we're going to do is we're going to let W be sort of the concatenation of X and X star. Right? And then the idea is that lots and lots of statistics that we're interested in, lots of functions that we would like to know, determine dynamics for, take a specific form in that they look like a function G applied to the matrix W transpose Q of KW, where Q is a polynomial, and K is your covariance of your data. So what do I mean by when I take W transpose Q W? It's just I'm forming sort of these 2x2 block matrices of the form like X transpose Q of KX, X transpose Q of KX star, etc. Now, this block matrix is low dimensional. Why? Because you've already killed off the D side. The D is the high dimensional side. Examples of this include stuff like the risk, the norm of the gradient, distance to optimality can all be represented in this way. Okay, so you might be like, is that actually true? Okay, so let's take some of our favorite examples. So let's look at least squares. So least squares would be something like I'm taking the trace of A transpose X minus my target, and then taking its expectation over the data. And if you write that out after taking the expectation, you get something which looks like trace of X minus X star transpose K, X minus X star. So that can be a polynomial with this W on each side. Maybe more surprising if you can do this for other objectives. such as things like logistic regression. So logistic regression is a classification. So it sort of outputs the probability that a given, say, picture, which would be your data A, lives as like a dog or a cat or whatever. If you write that as a problem, you can write it as a risk minimization problem in this form. And you might be saying, how is that written as some W or with a Q, K? It doesn't look like it. Well, it does work. Why? Because if you look at A transpose X, remember A is normally distributed with covariance K. So A transpose X is normally distributed, but now with a covariance given by X transpose KX. Okay? So if we look at things like the log of X of A transpose X plus 1, we take its expectation, well, we can just do sort of a change of variables and replace the A transpose X with something like the square root of its covariance times by just a standard normal. And then this function is clearly written as just a function of polynomial in between this W matrix. Is this clear? A little bit surprising, maybe, but it does work. So as I mentioned, again, lots of these statistics then can be written in this form. So because of this, it means that if we actually wanted to understand dynamics of, say, the stochastic gradient algorithm, we don't actually need to understand directly the dynamics of the statistic we're interested in. It's enough to first figure out the statistic or the dynamics of W transpose Q K W, that quantity, okay? And then just apply our statistic to it, because we can always write it in that form.
So Courtney, I have a question.
Yeah.
All of the statistics we're taking are of the data, and the randomness that's in the SGD algorithm doesn't appear to, it's not on display yet. Do the dynamics that are discussed here also go through for vanilla gradient descent? And maybe by doing stochastic, you don't deviate significantly from that?
That's a great question. Actually, so yes, you can view it as that. You'll get a slightly different dynamics, and I'll explain where they come up with the variance between gradient descent and SGD. So where does the SGD noise come up? But you're right. At this moment, technically, I could do everything for gradient descent with the data also. Yeah. Cool. Great question. Anything else? Okay. Right. Yeah. So basically, the idea is that we can just look at finding dynamics for W transpose Q of KW. That's statistic that defines everything. But we have to be able to do it basically for like lots of different Q functions, lots of different polynomials. So that becomes a problem because we have to do it for every Q. We have to use some trick. We won't be, we have to close the system. We can't have it for every Q, for every polynomial. So there's a trick that we use, which I hope the harmonic analysts in the room know and appreciate, which is that we can use the resolvent. So if we look at the resolvent of a matrix, it's given by Z minus K inverse, right? Where Z is a complex number, just not in the spectrum of K. And instead of looking at W transpose Q of KW, we can instead look at this new dynamics S, which is W transpose resolvent of KW. Okay, why is this useful? It's useful because if you know S, you essentially can recover any polynomial, and actually you can recover a lot more. You can recover analytic functions. Why is that? Well, you can just use Cauchy's integral formula. Gotta love Cauchy's integral formula. Super powerful, which is that you can write W transpose Q of KW as just the contour integral with Q of Z times the function, right? Okay, so here's where I have to deviate a little bit. Oh, sorry, maybe let me just explain this. Deviate a little bit from gradient descent. So in order to do SGD dynamics, you actually have to change time. And it's the reason which is that a gradient, a full gradient is like like order D size. So it's like in a bigger space. Like you need to do D iterations of SGD to get the same thing as a full gradient, a step of gradient descent. So here what I'm going to do is I'm going to set my iterates of SGD, K, to be equal to T times D. So I'm going to convert everything into a continuous time dynamics through this parameter T. Another way of thinking of it is T is equal to K over D, okay? Yes, K is discrete, but I'm going to pretend that you can kind of make a continuous version with this T. And what you can prove is that indeed you have sort of a high dimensional concentration, meaning that you can show that this S matrix will concentrate at SGD, will concentrate around a deterministic function with overwhelming probability. And for any statistic of it applied to SGD also concentrate to a deterministic function. Why? Again, what we'll see is that this deterministic function for S is going to be defined by an ODE. And as we just saw, well, every statistic that we're interested in is basically just a function of this S, so we can derive the deterministic thing for the statistics we're interested in as just taking G over a contour integral. And this works. So for instance, you could do things like phase retrieval. So here in phase retrieval, you're trying to find some unknown signal X star by only knowing things about the magnitude of it. So you get A transpose X in your data, you only know the magnitude, the square. You can formulate this as an optimization problem, and you can predict the dynamics of it. So that's what's happening on the left is the risk. But you also get a little bit more. Just so you know, if you start with a random initialization, then your sort of cross between your true signal and your X, your random initialization, X0, is basically 0 in high dimension. So you always tend to start along this line in this right picture at 0. This is the norm and the cross term. And you can see the evolution of how the norm and the cross term X transpose KX star is evolving over time. So basically what happens here in phase retrieval is that because of the random initialization, you kind of first try and solve sort of where the norms are equal, and then you solve for where the cross terms of the signal are. And you actually overshoot a little bit when you do that. So you don't quite go. Okay, any questions? Phase retrieval? All right, so how do we actually do this? Okay, so again, I'm doing this continuous time, and the basic idea is that we want to do calculus. Okay, so how do we do calculus? Well, because we create a continuous time, we need to create sort of an SDE. And so the idea is that we're going to construct a SDE, which is an approximation for SGD. It's going to be a new diffusion process. And basically the idea is that we're going to discretize our time by dimension. Okay, so not by step size, by dimension. Why is this useful? Well, we can keep step size quite large. All right. The other thing is if you want to make a sort of continuous time thing for SGD, the typical way of doing this is to make it so that your new process has the same mean and covariance as SGD. Okay? That's how you kind of do it. The standard way of doing these things. The problem with this in this case is that the covariance for SGD is extremely complicated. It's so complicated that you can't actually do it. Or you can do it, but you wouldn't be able to say anything about it. It's as hard to solve as SGD. So instead you say, well, maybe my goal isn't exactly for these two iterates to match. Maybe my goal is to create a diffusion process which just has that functions of the diffusion process are close to functions of SGD. Okay. And you can do that basically by reducing the complexity and the covariance and using high dimensionality. So it sort of reduces some of the complexity overall. And then you can show that indeed, this process is exactly what you want. It is the high dimensional equivalent of SGD. Okay, so any statistic under SGD will concentrate around the statistic under the diffusion process with overwhelming probability. Okay, so that's pretty cool. You can create this. How do you actually get the deterministic function out of all of this? I thought this was kind of fun. So you do homogenize SGD, you take this diffusion, and you just do calculus. So you do Ito calculus because it's an SDE. You've never done Ito calculus. It's just like calculus, but with extra rules for products and chain rule. It just has an extra rule associated with it. So you do it, Ito calculus on this. And what you see is like you get that d phi is equal to one term which is related to gradient flow or gradient descent, you want. And the second term is the result of Ito calculus. It's the result of the noise produced by Brownian motion, which is actually related to the noise produced by SGD. So in gradient descent, you wouldn't necessarily have the second term. Then you get a martingale term, but let's just ignore that term. The key idea here is that the gradient flow and the SGD noise can all be written as functions of this S matrix. Okay, so you might say, well, that's kind of cool. It's just a function of S. So if I wanted to create a closed system for everything, why don't I just take phi to be S? So if I let phi be S, then you can show that ds is actually equal to a function of S. And then you just say, okay, well, how do I create my deterministic equivalent? I'll just say that S is going to concentrate around some function, which is just a solution to that ODE. And this actually works. You can prove this is what's going on. So you just say the deterministic thing for S is just BS is equal to G of S. It's the solution to that ODE. And then you get everything. So you get that ds is G of S. That's sort of what you get from Ito calculus. You just replace the S with whatever the solution should be. And then you can also do the same with phi. Once you know S, you can just plug it in. And that's exactly how you get this result, that any phi applied to SGD will converge to something to phi of this diffusion. Then phi of this diffusion will concentrate around this deterministic function. So you might be saying, why is the resolvent so important in here? What's going on? Okay, so I thought this is kind of a fun exercise. Let's just see why you need the resolvent. So I'm going to let my S be this W transpose R at W. Let's look at the least squares loss because it's easier to write down. So remember, we could write it as this trace term. And let's just do Ito calculus where instead, well, maybe I thought I could actually do this with X transpose KX instead. So if I do Ito calculus with X transpose KX, all right, I have to take grad phi. Grad phi becomes KX. Grad R, well, that's also just something like K times X minus X star plus some other stuff. Okay, so I'm just doing the first term. What you get is X transpose K squared X sort of appearing. So the problem with using things like X transpose KX to close the system is that every time you take a derivative, you get sort of an extra K appearing here. The resolvent sort of solves this problem. This is the neatest trick for resolvent. And if you take the derivative with a resolvent inside, well, you still get KR plus stuff. But the trick is that you have an identity which always relates polynomials of K and R to each other. So you can take K, you just add and subtract Z. Then you have something like K minus Z with its inverse. That's just the identity. And then what are you left with? Z times the resolvent back again. So there's this neat identity that can take things like KR and relate it back to R again. And so that's how you can close the system, because you can replace this KR with something like I minus BR. And it's back as a totally deterministic thing of R, resolvent. So maybe if you didn't get anything out of this, just remember resolvents and matrices are really cool. So they work. They have all these neat little algebraic, cute things going on. Okay. So with that in mind, you might ask, okay, that's kind of cool. You can compute the deterministic dynamics. You have to solve this ODE, of course, but you can numerically solve it. But why is that really interesting? Like, you still going to have to run SGD. Well, it's interesting for various reasons. One of which is from an optimization question, you could ask what choice of learning rate sort of ensures that I actually decrease my optimality condition. Now, you can't decrease SGD at each iteration because of stochasticity and the gradients. It's not true that at each iteration you'll be able to decrease your distance to optimality. It's quite wiggly, as you saw. But you could ask this question of the deterministic function. You could say, what choice of step size guarantees that at each iteration from the deterministic function is actually just a monotonically decreasing function? All right, I'm doing distance to optimality. You can also ask this of risk, for instance, or even sort of, I guess, gradients, but that would be kind of weird. But okay, so what do? So you first need to write down what the deterministic equivalent of, say, is for distance to optimality, like x minus x star squared. And you just do that. Again, the way you create this deterministic function, you just apply Ito calculus to it. That's all I did. I just did Ito calculus on homogenized SGD, and you get two terms which are like A and I. And A you can re-represent as sort of an expectation, and I also as the expectation over your data. So the way you want to interpret this is that the A term is like gradient descent or gradient flow. The second term, the gamma t squared term, was the trace of K, is really representing the noise of SGD. That's the effect of SGD happening. So then you could say, well, if I want to make sure that I decrease at each iteration, I don't even need to solve this ODE. All I have to do is just ensure the D of it is less than 0. And so you can solve then for the gamma, the step size. And what you get is this term here. So what is this? So the idea here is that the functions of A and I, they really just involve F. So they have no dependencies on K and D. They're low dimensional. In least squares, it's like x squared, like something you can easily compute. The second thing you'll see is that it involves something like the trace of K over D. So the trace of K over D is like an average eigenvalue, which is appearing in here. So what this is saying is that the average eigenvalue is actually making an important role, not necessarily the largest eigenvalue, which is something that you would have in gradient descent bound. The other thing is A and I can be lower bounded based on convexity and smoothness assumptions. So if you assume things like strongly convex, then you have a lower bound on A and I, for instance. So in the least squares case, for instance, Q here is just exactly 1. So in some sense, it's exactly the critical threshold for step sizes. So when do you actually decrease at each iteration for a stochastic algorithm? You have a natural way of writing. You can also get convergence rates from this. So here, if I suppose F, so my little function, so the low dimensional function, it's easy to compute these quantities, is strongly convex and has elliptic gradient, then D squared decreases at a rate which is exponential. And you can take anything exponential with its convergence rate, which actually looks more like an average condition number. So its convergence rate, the exponential rate, is decreasing like lambda min of K, smallest eigenvalue of K, over the average eigenvalue. This is different than what you would traditionally get, which is more like the smallest eigenvalue of K over the largest eigenvalue of K. So this is really like all these problems, the average eigenvalue is playing a much, much bigger role. And in fact, for many of the data sets, the average eigenvalue of K is much, much smaller than the largest eigenvalue. So maybe you're actually getting a lot faster rate. This actually, like, you see this, you can actually see this effect. So here what I'm doing is I'm running logistic regression. I'm varying the learning rate, and I'm just plotting the last iterate. I'm just plotting what happens after running it 50 iterations for various learning rates. And I'm going to vary my covariance matrix so that I fix the trace of the average eigenvalue of it, but I allow the largest eigenvalue to vary. And if you do that, what you see is that, in fact, this average eigenvalue is playing a role, that as you go up to some fixed learning rate, which you can compute in this case, which is around 12, that independent, all these things have the same average eigenvalue, that they all end up sort of hitting this critical value at the same time. So indeed, this average eigenvalue is really, really playing a much bigger role compared to the largest eigenvalue, at least for criticality, guaranteeing that you're actually moving in correct directions for the optimization. Should pause here. Is this okay for everyone? Have I lost everyone? Everyone's very quiet here. Okay. Take a moment. Okay. So we can focus now. I'm now just going to focus on the least squares problem, a little bit easier problem, and look at some of the extensions that you can do. By the way, this leads to, I should maybe, before I begin, that leads to a very good question. It actually, this thing also tells you in some ways how to do line search. If you're interested, you just need to compute A and I by sampling. So you can create stochastic line search methods from this kind of stuff. Okay, but let me look at least squares problem and look at some extensions, which include things like multipath. Okay, so this is a little bit maybe easier to sort of see here, but I'm going to be, let's just minimize sort of the norm of ax minus b squared. And here I can write it as a large finite sum. And just as before, we're thinking of A as sort of being random and B being sort of a random vector. What is multipath SGD? Multipath SGD here is that you actually choose an index and then you compute the gradient with respect for that random index. So you take that ik, just choose one of those f sub i's, and you update in that direction. So you don't compute the full grad L, you just compute sort of one element of the sum. Just as before, you'll see that this version of it, so what's maybe the most different from what the past thing was, is that here you can reuse data. So the A's can be reused over and over again. The randomness is coming from choosing the index uniformly at random. Just as before, for large models, as you send the number of features and samples to infinity, but proportionally, you'll see that the loss will actually concentrate around a deterministic function. Okay? It's completely determined by the spectrum of the Hessian. Okay? And there's a homogenized SGD for it. So there's this diffusion process. And you see again that same picture on the left here, where I run different SGD runs for various sizes, and you see that the variance of the shaded region is actually going down as the size gets larger. So you might have said, well, I had this sort of Gaussian assumption on my previous data. How do you actually remove can you remove that Gaussian assumption? And here you actually can quite easily. So the way to remove it, or one way of removing it, is that in reality, you actually only need something called delocalization of the eigenvectors of A transpose. So what does this mean? This means that the eigenvectors are not aligned with coordinate axes. So you don't have sort of concentration in certain directions. The eigenvectors of A transpose are spread out. So classic example of this, you take an A whose entries are normally distributed. Then if you form the matrix A transpose, its its eigenvectors are uniformly distributed on the sphere. The classic example of this. But it turns out that lots and lots of high-dimensional random matrices also satisfy this property. It's random matrices like to prove this result. So lots of things satisfy it. So for instance, sample covariance matrices satisfy it, okay, provided that your covariance is on the feature side. Random features satisfy it. So this is where you take products of two random matrices and then you apply an entry-wise function to those products. So you use that as your A, that also satisfies this. This random features is a mimic of two-layer neural networks. So there's lots of things that satisfy this thing. And that's actually all you need to get the concentration. The other thing is you can then compare what happens when you apply sort of this empirical thing, the thing where you reuse the data in comparison to that risk function that you saw before, but where you still train your X using the empirical one. Right? And you can just completely predict all the dynamics. So here I'm predicting it on real data using MNIST. Okay, the training, that empirical, that sum versus comparison with the expected. Oops. Oh no, I lost it. Sorry, everyone. I hit the wrong button. Oh no. Okay. Where did it go? Okay, hold on. Sorry. I moved my screen off to the side. Now I don't know where my screen is. Let me just restart.
If you go back into the hot corner that brought up the kind of panel on top, you should just be able to click back onto your slides.
Is that where it goes? Where did it go? Okay, hold on. Maybe I'll just do it the old. I'm not super technology. I work at Google, but I'm actually not that great at computers, ironically. Oh, there it goes. Okay, perfect. Good. Okay, thanks. Okay. You can do other things for this too. You can analyze things like step sizes. So you can actually analyze behavior of step sizes. And when you can see things, it's like phase transitions. So the idea here is that there exists sort of a step size for which when you're below the step size, you look like gradient flow, like you just behave like gradient flow in terms of its convergence. And then above it, the noise of SGD starts to play a role and you start to get different behavior. So you get these sort of sharp phase transitions as you vary the step size and the convergence rate. And this is not a smooth function. So there is actually, it's continuous, but not continuously differentiable. There's actually a jump in the two. Okay. But if I have a little bit of time, maybe I can talk a little bit about large batches. You can also do this for momentum and look at momentum parameters. Here, I'm going to actually do a batching effect. So I'm actually not just going to use a single index. I can use a batch of indices to create my estimate for my gradient. You still get the same concentration. The main difference here is that things are not continuous, they're in discrete time. So this would be the effect sort of same thing with gradient descent. You actually cannot create a continuous time version of this. It would always be discrete. You can analyze effects, get how you should choose momentum and step size parameters. Very fun. Here, the idea is that there's two sort of competing forces, one which is looking like something like gradient descent with momentum, and one which is looking like the SGD noise. And so what happens is that the SGD noise only actually starts to affect the convergence when you have certain parameters. If you're below, so this is what this middle picture is, you're in the black region here, this is where SGD noise has no effect. SGD noise only hits you once you jump over and for these specific parameters. Then you can get the convergence rate just by taking the max. You can see how the batch fraction affects the region of convergence over time, which is what's happening in the bottom here. You can also get things like near optimal parameters. So again, the average condition number is going to play a role here. So that's the trace over the smallest eigenvalue. And you can write down exactly how to choose your step size and momentum parameter. And you get to see exactly the effect of batching has here. So batching here is my zeta, my batch fraction. And then I'll just end here with the effect that you can do because your convergence rate depends on these two quantities, one of which is like has a batch effect, and one which is like classical sort of momentum algorithm, 1 over square root of kappa. You can also ask, well, it means that there has to be a transition where you take a large enough batch and you actually switch over from behaving like things like SGD, where you're only getting an average condition number convergence, to something which has like the classic accelerated rate of 1 over square root k. And so that actually occurs if you balance these two terms off at exactly the average condition number over the square root of the classic. And so what do I mean by that is that when your large batch is actually bigger than this ICR ratio, okay, it means that SGD plus momentum actually gives you an accelerated rate of 1 over square root of kappa. Gives you the classic full batch momentum rate. See a speed up. When you have small batch, you just get SGD, right? And what this also says is that there's like a batch saturation effect, precisely where your batch fraction is equal to your ICR, meaning that if you add more to your batch, add more of these grad S to your batch, you don't get any improvement in the convergence rate. Just completely determined. It stops moving. So that's actually what you see in this picture on real data. I'm varying the batch size, and I'm looking at just what happens at the last iterate. And what you see here is that as you increase, there's like a moment where all of a sudden the last iterate doesn't change very much, and that's because you reach sort of the ICR. Yeah. So I think I'll end here. I'll just say, sorry, I would pass, but here is everything. And here's all these papers that everything is related to. So thank you for inviting me. Okay.
Awesome. I'm going to express my appreciation by clicking a button like that. I'll stop.